Good evening, everybody. It's Thursday, May 28th, and this is Nighttime Mathematics Radio. Now, the show has the usual format. Tweet your questions into @NightMathRadio, and we'll try to answer them live on the air. So, for the last couple weeks of the term here, where we're all trying to power it through to a close, even though the classes have all gone somewhere else. You can see them on Zoom, but they just don't seem to happen in real life anymore. But the homework stays very, very real. So, for the moment, tweet your questions to @NightMathRadio on Twitter. We'll take a minute or two to see if anyone tweets anything in, and then we'll get right to your questions. This is Nighttime Mathematics Radio. Welcome back, everybody. This is Nighttime Mathematics Radio. Well, we got what's very specific kind of question today. These questions come up when you're trying to solve a problem where you're trying to find the volume of a surface where you're given the base and some sort of cross-sectional area. So let's take a look. So a typical setup for these problems looks like this. You're given some sort of base. You're told, for example, we're looking at the region in the first quadrant, bounded above by the square root of x and below by x squared. Well, you sort of know what those curves look like, right? The square root of x looks like a parabola set, the top half of a parabola set on its side, so it looks like this. And x squared looks like an open parabola moving upwards. Looking at the first quadrant, so I don't care about the left half, so it looks like this. And they cross right here at 1, 1, because 1 squared is 1, the square root of 1 is 1, so 1 is sort of 1, 1 is sort of this interesting point. So, and they say it was bounded above by the square root of x and below by x squared, which means we're interested in this region right here. Then we're told the cross-sectional area is perpendicular to the y-axis. So as you move up the y-axis and look this way, look like squares. So if you could tilt your head sideways, which we can't really do because I'm not very good at perspective drawing, you'd have little teeny squares at the ends, great big squares in the middle, and you have to figure out the volume. So how on earth do you do this? Well, the answer is we know how big the square is. So what you do this essentially by looking at Riemann sums. You say, well, if I were to approximate this, what I'd do is I'd say, well, how big is the square at some height y? Well, the side of the square is this distance right there, which runs from, on the right, x squared, and on the left, square root of x. But if y is equal to the square root of x and y is equal to x squared, you notice here, this is a function of y. The thing we're given is that these things are perpendicular to the y-axis. So what we want is the area of the square at y, some specific y value. So I don't really want y equals square root of x, I want things the other way around. If y is equal to square root of x, then x is equal to y squared. Remember, we're in the first quadrant here, so x and y are both positive, so I don't have to sit and worry about, oh gosh, what if the value is actually negative, then if we can't take a square root, oh, headache, headache, headache. We don't have to worry about it. So the curve on the left, on the right here, I should say, was y equals x squared, so it's x is equal to the square root of y. And the position on the left here is y equals the square root of x, so x is equal to y squared. And we want the side of the square. We want that distance. And the way you get a distance is, as always, you subtract the right endpoint from the left endpoint. So the distance, that's the side of the square at height y, is equal to the square root of y minus y squared. So what's the area of the square? The area of the square at that position y is square root of y minus y squared, quantity squared. Now, how do we turn this into an integral? And the way we do this is we think, okay, how would I approximate this? If I wanted to approximate the volume, what I would do is I'd pick a bunch of specific y values, say y sub I, and sum from I equals, say, 1 to n for some number of I values. The area of the thing at y sub I. Then what I do is I make I'd make sort of a little rectangular box out of it by multiplying that by the delta y, by the distance between the two y points. And so that's going to be an approximation, and then this will become more and more accurate as I take the limit. In fact, it will become perfectly accurate if I take the limit, the delta y goes to 0, and this is precisely a Riemann sum. So the volume is equal to, in the limit, the Riemann sum becomes an integral from 0 to 1, a of y dy. So in the limit, the volume is just equal to the integral from 0 to 1 of square root of y minus y squared dy. And this is how you do every problem like this. The key thing is to be very, very careful. Remember what the thing looks like in the cross-section. It can be very easy to make simple mistakes by just not paying quite enough attention to what's happening in the cross-section. So really work out the thing. So if it's a cross-sectional area is a square, figure out what the side of the square is. If the cross-sectional area is a semicircle, figure out the radius of the semicircle. First work out the diameter, because the thing we've looked at is a diameter. Take half of that to get the radius. Remember, the area of a semicircle is 1/2 pi r squared. That's like the most common student mistake, is you forget that you're dealing with semicircles, so just put pi r squared in because you're so used to typing pi r squared. You're done. And this you can see you can easily integrate out. You just square out the thing in parentheses here. So we get v is equal to the integral from 0 to 1 square root of y squared, which is y. Math is so easy in the first quadrant. Minus 2y to the 5/2, because it's, after all, y squared times y to the 1/2. It's y to the 5/2, plus y to the 4th dy. This is easy. We can integrate this term by term. That's 1/2 y squared minus 2 times 2/7 times y to the 7/2 plus 1/5 y to the 5th, evaluated from 0 to 1. You notice all of these are very easy because the y factor in each term is 1 at the upper thing and 0 at the bottom, so we only have to worry about the upper one. So this is 1/2 minus 4/7 plus 1/5. And so this whole mess just boiled down to some simple fraction math. 7, 5, and 2 are all relatively prime, so the denominator is going to be 70. So this is 35/70ths minus 40/70ths plus, let's see, multiply it by 14, so 14/70ths. So this is, let's see, 35 plus 14 is 49 minus 40. So this is 9/70ths. And we're done. That is literally every problem like this. The key thing is to be very, very, very careful to label what you're doing. It's to be very, very careful to remember what's going on. The easiest thing to make a mistake here is just to lose track of what you're doing. As long as you don't do that, you'll be fine. And this is Nighttime Mathematics Radio. Let's see, do we have anything else on Twitter tonight? Looks like we don't. So that will be the end of tonight's show. Again, keep tweeting the questions in to Night Math Radio on Twitter. I'll answer questions live on the show when I get them. For now, everyone stay safe out there in this strange world where the classes are all somewhere on Zoom, but the homework just keeps coming. We'll be running this show nightly till June 12th. Then over the summer, we'll take a break and post some pre-recorded shows. We'll be back for you in the fall. This has been Nighttime Mathematics Radio. Good night, everybody.